Right now, sitting in your pocket, orbiting above your head, and potentially inside a hospital down the street, quantum technology is already working, quietly, invisibly, and it has been for decades. Not quantum computing, the flashy, still experimental technology dominating headlines. Something different, something already fully operational, already inside your daily life, and almost nobody talks about it. It is called quantum sensing, and the moment you understand what it actually is, you will realize you have been relying on it every single time you have ever used GPS. Let's start with the device sitting in your pocket right now, because this is genuinely the easiest way to understand what quantum sensing actually means in practice. Every time you open Google Maps or Waze, your phone talks to satellites orbiting roughly 12,000 miles above Earth. And those satellites determine your exact position by measuring tiny differences in how long it takes signals to travel from multiple satellites to your specific location. That measurement only works because of something ticking away inside every single GPS satellite, an atomic clock. And atomic clocks are quantum sensors. Full stop, no asterisk, no future tense required. Here is how that clock actually works, and it is worth understanding the mechanism because it explains why this counts as genuine quantum technology rather than just clever classical engineering. Inside these clocks, atoms of cesium or rubidium naturally vibrate at an extraordinarily precise, extraordinarily stable frequency, a frequency determined directly by quantum mechanical properties of the atom itself, rather than by any mechanical or electronic component that could drift, wear out, or lose accuracy over time the way a conventional clock eventually does. These atomic references are so stable that the primary time standard built on this exact physics loses roughly 1 second every 100 million years. That level of precision is not a nice-to-have feature. It is the entire reason GPS works at all, since a timing error of just a few billionths of a second translates directly into a positioning error of several feet on the ground. Every time your phone tells you exactly where you're standing, you're relying directly on quantum mechanics, whether you have ever thought about it that way or not. This is exactly the point that gets lost in most casual conversations about quantum technology, and it is worth stating clearly because it reframes an entire technology category most people assume is purely futuristic. What scientists sometimes call the first quantum revolution already happened decades ago, and it gave the world the transistor, the laser, and the atomic clock. Foundational technologies now so deeply embedded into ordinary devices that almost nobody thinks of them as quantum technology anymore. Even the MRI machine used in hospitals to scan the inside of your body relies directly on quantum mechanical principles, specifically a phenomenon called nuclear magnetic resonance, where the quantum spin states of hydrogen atoms inside your body respond to a powerful magnetic field in ways that let doctors build an extraordinarily detailed image of your internal anatomy without ever needing to cut you open. If you have ever had an MRI, you have personally experienced quantum sensing technology doing genuinely life-saving diagnostic work. Now, here is where the story gets genuinely exciting, because what is happening today represents something researchers call a second quantum revolution, and the distinction matters enormously for understanding where this technology is actually headed next. The first generation of quantum-enabled devices, your MRI machine, your GPS satellite's atomic clock, generally exploit quantum mechanics somewhat indirectly, taking advantage of quantum effects happening at a large, aggregate scale, without deliberately engineering and controlling individual quantum states. The current generation of quantum sensors, by contrast, is explicitly designed from the ground up to manipulate individual atoms, individual photons, and individual quantum states directly, pushing measurement precision to limits that are, quite literally, the best that the laws of physics will ever allow for that specific type of measurement. This next generation quantum sensing revolution is not confined to research labs anymore in understanding exactly how far. It has already spread into active commercial and government use is genuinely the entire point of this video. Vector Atomic, a company recently acquired by the quantum computing firm IonQ, has developed atomic clocks and inertial sensors currently deployed on submarines, aircraft, and even the Department of Defense's classified X-37B orbital spaceplane, delivering what the company describes as a 1,000 times improvement in GPS accuracy compared to conventional systems. That is not a laboratory demonstration running under carefully controlled conditions. That is operational hardware, currently flying, currently deployed, currently generating over $200 million in confirmed United States government contracts. The specific problem this next generation quantum sensing is designed to solve deserves real attention, because it explains exactly why militaries and increasingly civilian industries are investing so heavily in this technology right now. GPS, for all its everyday convenience, has a fundamental weakness. It depends entirely on receiving a clear, unobstructed signal from orbiting satellites. Step into a tunnel, walk between tall buildings in a dense city, or find yourself in an environment where an adversary is deliberately jamming or spoofing GPS signals, exactly the kind of electronic warfare conditions increasingly common in modern conflict zones, and conventional GPS navigation simply stops working. Quantum inertial sensors, specifically quantum gyroscopes and accelerometers built using a technique called atom interferometry, solve this problem in a genuinely elegant way by measuring acceleration and rotation directly, using the wave-like properties of ultra-cold atoms themselves, allowing a vehicle, a ship, or a drone to continuously track its own position with extraordinary precision, even when every external signal has been completely cut off. If you're finding this breakdown useful, go ahead and hit that subscribe button, because we cover stories exactly like this every single week, connecting the dots most channels leave scattered. Beyond navigation, quantum sensing is quietly reshaping several other fields that most people never think to connect back to quantum physics at all, and each one deserves a closer look on its own terms. Take magnetometers, quantum sensors specifically designed to detect and measure magnetic fields with extraordinary sensitivity. These devices are already being used for brain imaging, detecting the astonishingly faint magnetic fields naturally produced by electrical activity inside the human brain, offering researchers and doctors a genuinely non-invasive window into neurological activity that complements, and in some cases exceeds, what conventional imaging techniques can reveal. The exact same underlying magnetometer technology is simultaneously being deployed for geological exploration, helping mining and energy companies detect underground mineral deposits and geological formations with a level of precision that conventional survey equipment simply cannot match. Gravimeters represent another genuinely fascinating branch of this same technology tree. Quantum sensors specifically engineered to detect minute variations in gravitational force, variations so subtle they would be completely undetectable using any conventional measurement instrument available today. NASA has already flown a quantum gravity sensor to space in partnership with the company Infleqtion, demonstrating this technology's readiness for genuinely demanding, real-world deployment well beyond the comfortable, carefully controlled confines of a university physics laboratory. On the ground, the same underlying gravimeter technology is being explored for subsurface mapping, helping identify underground infrastructure, detect hidden voids or tunnels, and locate valuable mineral deposits, all without ever needing to physically dig into the ground to find out what is actually down there. There's also a genuinely important, if less flashy, story unfolding around chip-scale atomic clocks specifically, because it captures exactly how quantum sensing technology tends to spread from expensive, specialized military applications into increasingly ordinary, increasingly affordable everyday use. A chip-scale atomic clock, sometimes abbreviated as a CSAC, is a fully functional atomic clock miniaturized down to a volume smaller than a single cubic centimeter, made possible by advances in micro-electromechanical systems. Manufacturing that shrink the vapor cells these devices rely on by roughly 100 times compared to older, bulkier designs. These chip-scale clocks are already widely deployed inside military GPS receivers, uncrewed aerial vehicles, and secure communications equipment, and companies including Microchip Technology already produce the most widely used commercial version of this exact hardware. A startup called Mesa Quantum is now specifically working to push this same underlying technology down into consumer-scale devices, phones, wearables, and even data center infrastructure, aiming to reduce unit costs from several $1,000s down to just a few hundred, exactly the kind of cost curve that historically determines whether a genuinely useful technology stays confined to specialized government contracts or eventually spreads into products ordinary consumers actually purchase and use. Mesa Quantum's own leadership has been refreshingly direct about the scale of ambition sitting behind this specific miniaturization effort, describing a future where people eventually look back on today's satellite-dependent GPS as a genuinely archaic way of doing things, once chip-scale quantum sensors become cheap and small enough to embed directly inside everyday consumer electronics rather than remaining confined to specialized military and aerospace hardware. That kind of prediction obviously deserves healthy skepticism, since ambitious startup founders routinely describe their own technology in the most transformative possible terms. But the underlying trajectory the company is describing, atomic clocks shrinking from laboratory scale to briefcase scale to chip scale over a period of just a few decades, mirrors almost exactly the same miniaturization curve that took computers from filling entire rooms to fitting comfortably inside your pocket. And that historical parallel is worth taking seriously, even while remaining appropriately cautious about specific timelines. Telecommunications infrastructure represents another quietly essential application of this same underlying atomic clock technology, one that almost nobody outside the industry ever thinks about, despite relying on it constantly. The same extraordinarily stable timing references that make GPS possible also underpin the synchronization protocols that keep the broader internet functioning correctly. ensuring that data packets arrive in the correct sequence, and that financial transactions, phone calls, and countless other time-sensitive digital processes remain properly coordinated across networks spanning the entire globe. Every time you make a phone call, stream a video, or complete an online purchase without any noticeable synchronization glitch, you are indirectly benefiting from exactly the same quantum mechanical atomic clock technology that keeps GPS satellites accurately synchronized, working invisibly in the background of digital infrastructure most people never have any specific reason to think about. There's a broader economic story worth including here as well, because it helps explain why government and private investment in quantum sensing has been accelerating so rapidly in recent years, even while quantum computing continues generating the overwhelming majority of mainstream media attention. Industry analysts project the broader quantum sensor market could generate close to $2 billion in annual revenue by the mid-2040s, growing at a steady, sustained pace over the next 2 decades, driven specifically by expanding applications across navigation, medical imaging, defense, and industrial exploration. That kind of durable, multi-decade growth projection reflects a technology that industry analysts view as fundamentally different from a speculative, still unproven bet, precisely because so much of quantum sensing's core value has already been repeatedly, verifiably demonstrated in active, real-world deployment rather than remaining a purely theoretical promise still awaiting its first genuine commercial success story. Defense investment specifically has been accelerating across multiple countries simultaneously, another signal worth noting, given how consistently international competition tends to predict where a given technology is genuinely headed next. Government programs in the United States, United Kingdom, China, and across the European Union have all been actively accelerating quantum sensing development timelines, treating the technology as a genuine strategic priority, rather than as purely speculative research investment. IonQ's decision to specifically acquire Vector Atomic in October of 2025, rather than simply partnering with an outside sensing company, signals that established quantum computing firms increasingly view sensing not as a peripheral side project, but as a core, directly monetizable commercial opportunity worth building in-house, alongside their more headline-grabbing quantum computing ambitions. It is worth being honest about where real limitations still exist here, because a responsible look at this technology should not overstate how far quantum sensing has already traveled toward completely ordinary consumer deployment. Many of the most advanced quantum sensors currently in active use, particularly optics-based magnetometers and gravimeters, still require genuinely substantial physical infrastructure, refrigeration systems, precision optics, and delicate laser setups that can occupy a space roughly the size of a dining room table in a research laboratory setting. Much of the ongoing engineering effort inside defense research laboratories, including work happening at facilities like the United States Naval Research Laboratory, is specifically focused on solving exactly this miniaturization challenge, shrinking these devices down enough to fit inside a submarine, an aircraft, or eventually a handheld device without meaningfully sacrificing the extraordinary precision that makes the underlying quantum physics worth exploiting in the first place. Aviation represents one of the more immediately promising near-term applications actively being explored right now, and it helps illustrate exactly why solving that miniaturization challenge matters so much in practice. Commercial airlines and aerospace manufacturers have expressed genuine interest in quantum inertial sensors, specifically because they could meaningfully improve aircraft positioning accuracy during the exact moments when satellite navigation becomes least reliable, near mountainous terrain, inside dense urban airspace corridors, or in any scenario involving deliberate signal interference. Unlike consumer smartphone applications, which can tolerate occasional positioning uncertainty without serious consequence, aviation demands the kind of continuous, unbroken positioning reliability that quantum inertial navigation is specifically designed to provide, making it a genuinely natural, high-value early adopter for this maturing technology well before it reaches broader consumer markets. Single photon detectors round out this broader landscape of already deployed quantum sensing technology, and they represent yet another category most people have never heard of, despite encountering their effects regularly. These devices measure the interference patterns of individual photons of light, enabling detection of displacement, temperature, or velocity changes so small that conventional optical instruments simply cannot register them at all. This exact technology underpins advanced astronomical instruments used to detect extraordinarily faint signals from distant objects in space and increasingly finds its way into advanced manufacturing quality. Control systems, where detecting microscopic defects and precision-engineered components can mean the difference between a safe, reliable product and a catastrophic failure down the line. Much like atomic clocks and magnetometers before them, single photon detectors began their journey confined to specialized physics laboratories before, gradually working their way into genuinely practical revenue-generating commercial applications. following almost exactly the same maturation pathway that has defined quantum sensing's broader, quietly successful expansion into everyday infrastructure over the past several decades. What makes quantum sensing genuinely different from its more famous cousin, quantum computing, and worth understanding as its own distinct, considerably more mature technology category, is a specific structural advantage that industry analysts have pointed out repeatedly. Quantum computing needs to prove its usefulness against an extraordinarily capable, deeply entrenched incumbent, classical supercomputers that have had over 70 years of continuous engineering refinement behind them, and matching or exceeding that entrenched performance requires millions of stable, error-corrected qubits working in concert. A milestone still meaningfully years away by even the most optimistic industry timelines. Quantum sensing faces no such uphill technical battle. A single trapped ion can already function as a genuinely useful atomic clock. A modest cloud containing just a few hundred atoms can already serve as an effective magnetometer or gravimeter. Quantum sensors do not require the kind of massive scale or the kind of large scale entanglement that quantum computing fundamentally depends on, which is precisely why quantum sensing has already reached genuine revenue-generating, operationally deployed status years, in some cases decades, ahead of quantum computing's own more distant, still uncertain commercial timeline. There's also a broader philosophical point worth sitting with as we wrap up, because it reframes how we should probably think about emerging technology more generally, not just quantum sensing specifically. The most transformative technologies rarely announce themselves with a single, dramatic headline moment. They tend to arrive quietly, embedded inside infrastructure most people never think to examine closely, doing genuinely essential work behind the scenes for years or even decades before enough. People notice and start connecting the dots. Atomic clocks have been silently running GPS satellites since the technology first launched decades ago. MRI machines have been using nuclear magnetic resonance to save lives since long before most patients ever thought to ask what physical principle actually makes that diagnostic image possible. Quantum sensing, in this specific sense, is not really a story about the future at all. It is a story about technology that has already arrived, has already proven itself indispensable across navigation, medicine, defense, and telecommunications, and simply never received the kind of dramatic, headline-grabbing introduction that makes people stop and take proper notice. So the next time you glance down at your phone's GPS navigation, remember exactly what is actually happening behind that little blue dot showing your location. An atom of cesium or rubidium orbiting Earth inside a satellite, vibrating at a frequency governed directly by the laws of quantum mechanics, precise enough to lose only 1 second every 100 million years, quietly making modern navigation possible in a way that has absolutely nothing to do with any exotic quantum computer you might have read about in a more sensationalized headline. Quantum sensing is not some distant future technology waiting patiently in a laboratory for its eventual big commercial debut. It has been running quietly in the background of ordinary life for decades, and it is only getting more precise, more compact, and more deeply embedded into daily existence with every passing year, whether or not most people using it ever stop to notice. If you want to keep exploring the quieter, already operational side of quantum technology, the side that rarely gets the same breathless headline treatment as quantum computing, make sure you like this video and subscribe, because there is a lot more quantum technology already hiding in plain sight than most people realize, and we are going to keep finding it.